Captions in English, please. So this is the 7th video on chapter 12, and it's about molecular shape or molecular geometry. So let me start with a story on artificial sweeteners, which will show you how our taste buds are fooled by molecular shape. So artificial sweeteners such as aspartame taste sweet but have a few or no calories. And taste and caloric values are entirely separate properties of food. The caloric value of a food depends on the amount of energy released when the food is metabolized, which means when the food is digested, broken down into smaller pieces, and then, absorbed into the blood. Sucrose, table sugar, is metabolized by being oxidized and forming carbon dioxide and water, according to the following chemical reaction. So C12H22O11 is oxidized by using oxygen, that is brought to the cells when we breathe. And then this oxidation releases a lot of energy. And the waste product are carbon dioxide and water. And so some artificial sweeteners, such as saccharin, are not metabolized at all. They pass through the body unchanged and therefore have no caloric value, right? They are not digested, they are just, expelled. Other artificial sweeteners, such as aspartame, are metabolized but have a much lower caloric content for a given amount of sweetness than sucrose. So it is broken down, but it gives much less energy than sucrose. And so the surface of a taste cell on our tongue contains specialized protein molecules called taste receptors. And each molecule that we can taste fits snugly into a special pocket on the taste receptor protein called the active site based on its shape. So our taste buds, are welcoming the molecules, and if the shape matches a given taste bud, it will tell us, oh, this tastes sweet and this tastes salted, etc. And artificial sweeteners taste sweet because they fit into the receptor pocket that normally binds sucrose. So they fit into the pocket for the sweetness, which is adapted to the molecule of sucrose. And both aspartame and saccharin bind to the active site of the protein more strongly than sugar does. So they fit in there much better. So they will really trigger the sensation of sweetness. So for this reason, artificial sweeteners are sweeter than sugar. It takes 200 times as much sucrose as aspartame to trigger the same amount of nerve signal transmission from the taste cells. So you see how our taste buds are fooled by molecular shape. So shape of molecules is an important property. And so Lewis theory, in combination with the valence shell electron pair repulsion theory, which is symbolized by VSEPR, so valence shell electron pair repulsion theory, can be used to predict the shapes of molecules. And it's an easy way to do it. And so as VSEPR theory says in the name, it's based on the idea that electron groups, and so an electron group can be either a lone pair, a single bond, a double bond, or a triple bond. Each of these are considered one electron group. And so those electron groups, they repel each other. Remember how electrons are negatively charged, and like charges repel each other, and so electrons repel each other. And so as you see in the schematic here, the electron groups, which are bonds here, pairs of electrons between atoms, they repel the electrons from another bond, etc. And so this repulsion between the negative charges of electron groups on the central atom determines the geometry of the molecule. So you will focus on the central atom to determine the geometry of the molecule. And so this is the molecular geometry chart. Molecular geometry is synonymous to molecular shape. So read this as the shape. And so so the number of electron groups, you need to count it on the central atom only. So you focus on the central atom of your molecule and read the number of, or see the number of electron groups from the Lewis structure. And from there, you will look at a row where there's 2 electron groups or 3 or 4. And then depending if your central atom has a lone pair or not, it will lead to a different molecular shape. And there are models to show you what it means. And the bond angles are given. The bond angles are the angles between 2 bonds. So we will go over each of these separately, one by one. So what is the molecular geometry when the central atom has 2 electron groups? Example, CO2 has this Lewis structure where carbon has 2 double bonds. So if you look at carbon, the central atom, it's surrounded by 2 electron groups. Each double bond is 1 electron group. And so for these 2 electron groups to be as far away as possible from each other, the best way is to be exactly opposite each other around the carbon. And so that leads to a linear geometry with an angle of 180 between the 2 angles, between the 2 bonds. So that's the simplest one. What is the molecular geometry when your central atom has 3 electron groups? For example, Br3, boron bromide, has 3 electron groups around the central atom. If you look at the electron dot formula here on the left, you can see that boron, the central atom, has only 3 single bonds around it. Remember how boron only needs 6 electrons to be satisfied. And so those 3 electron groups will try to be as far away from each other as possible, and this will lead to a trigonal planar geometry. Trigonal planar. Trigonal because it's in the shape of a triangle, and planar because all atoms are in the same plane. It's a flat structure. And the angle between 2 bonds, 2 consecutive bonds, is 120 degrees. So between each of the bonds, you have 120 degrees. So it's a symmetrical structure. And now what is the molecular geometry with 3 electron groups around the central atom, including a lone pair? So in a molecule of SO2, sulfur has 3 electron groups. If you look at its electron dot formula here on the left, you can see that sulfur is the central atom and it's surrounded by 1 single bond, 1 double bond, and 1 lone pair. So each of these is an electron group. And among those electron groups, there is a lone pair, and this will change the shape that you see. So repulsion is minimized with the 3 electron groups at angles of 120 from each other, just like the previous shape. A trigonal planar arrangement is what will minimize the repulsion between the 3 electron groups. However, because there is that lone pair, there is no atom bonded to that lone pair, then the shape of the molecule will not show that there is an electron group there, and it will look bent. The shape is determined only by the 2 atoms of oxygen bonded to sulfur, and it will be bent with a 120 degree angle between the 2 bonds because it's a trigonal planar arrangement, but you're missing one atom from the previous shape, from the previous slide. So then it looks like that. It looks bent with an angle of 120 between the two SO bonds. And what is the molecular geometry when your central atom has 4 electron groups around it? For example, CH4, carbon tetrachloride, methane, CH4 is methane. Methane, the Lewis structure is given on the lower left side here. And you can see that carbon is surrounded by 4 single bonds. And so each single bond is an electron group, and that's 4 electron groups around carbon. For these 4 electron groups to be as far away from each other as possible, they need to take a tetrahedral geometry. And so the angle between each bond is 109.5 degrees. So it doesn't matter the way you hold the tetrahedron. If you switch from one hydrogen, move it up, take another hydrogen, move it up, you will always, it will always look like that tetrahedral shape you see there. It's a symmetrical shape. The bond angles between 2 consecutive bonds is always 109.5. And so this is called the tetrahedral geometry. And we draw them on paper like what is shown on the right side of the slide here. Carbon and 2 hydrogens are in the plane, and so the straight lines are showing bonds that are in the plane. So the plane of the paper is the plane where you have the 2 hydrogens and the carbon. And then the hydrogen with the filled wedge is a bond coming towards you. And then the other hydrogen with the hashed wedge is a bond going away from the plane of the paper. So it's like a tripod at the base of the tetrahedron, and then there is a bond going straight up vertically. What is the molecular geometry with 4 electron groups when one of them is a lone pair? The molecule of NH3 has 4 electron groups like that, and 3 electron groups are from the 3 single bonds with those 3 hydrogens, and then 1 lone pair on the nitrogen. If you look at the Lewis structure here, you see nitrogen is the central atom, and it's surrounded by 4 electron groups, among which 1 is a lone pair. And so the lone pair still exerts its influence on the bonding pairs, and so the repulsion is minimized like if it was 4 electron groups, and it's then minimized in a tetrahedral arrangement. However, the shape of the molecule you see is a trigonal pyramid, because from earlier when you had a tetrahedron, you had a trigonal pyramid, and then you had a bond going up, straight up vertically. Well, now you remove that bond because it's a lone pair instead, and that lone pair, is not showing up in the shape of the molecule. There's no atom there to visualize it. So then it looks like a trigonal pyramid shape. So trigonal because the base of the pyramid is triangular, and pyramid because it's a pyramid. And so the bond angles are still close to 109 degrees, but slightly smaller. So sometimes you will see that it's labeled as 107 degrees. And so if we want to draw this on paper, you look at the figure on the right side, the trigonal pyramidal wedge dash notation. And so it's the same as base as the tetrahedron, except you do not draw the bond that goes vertically and that it was in the plane in the tetrahedral figure. This time it's gone, and you only see the base of the pyramid. So one bond is in the plane, it's the straight line, and then the full wedge coming towards you, and then the hashed wedge going away from the plane of the paper. Now, what is the molecular geometry with 4 electron groups, including 2 lone pairs? So sometimes you have 2 lone pairs. That's the example of water. Water, if you look at its Lewis structure here in the center of the slide, you see that oxygen, the central atom, is surrounded by 2 single bonds and 2 lone pairs. So that's 4 electron groups. Each lone pair is an electron group, and each bond is an electron group. And again, those 4 electron groups will minimize repulsion in a tetrahedral arrangement. However, 2 of these electron groups are not visible in the shape of the molecule, and what we see is a bent shape with bond angles slightly smaller than 109 degrees, even as low as 105 degrees for the molecule of water. And so then this time you can draw it on the plane. So the Lewis structure as you see it is what you would draw on the paper for water, because you can have all the atoms, the 3 atoms in the plane and the 2 bonds in the plane, and so drawn as single lines. Okay, so let's check that you can use this information to predict the molecular shape and bond angles of a few molecules. So you're given the Lewis structures, but you know, in practice, in your homework, for example, you will have to determine the Lewis structure before you can determine the shape. So the first step would be to determine the Lewis structure. And then from the Lewis structure, localize the central atom. And so we will start with the molecules on the left. And so please pause the video and work this out on your own before you watch the answer. So CS2 here, the central atom is the carbon. Carbon is surrounded by 2 double bonds. So that's 2 electron groups. When you have 2 electron groups, according to the table, you have a linear shape with a 180-degree angle. So it's linear with 180-degree angle between the 2 bonds. pH3, the molecule below. So P phosphorus is the central atom. It's surrounded by 1, 2, 3 single bonds plus 1 lone pair. That's 4 electron groups. If you look at the table, 4 electron groups lead to, yeah, let me show that. So 4 electron groups, and there was 3 single bonds and 1 lone pair. So you need to look at the line where it says 4 electron groups, 1 lone pair. And the molecular geometry is trigonal pyramid with angles slightly less than 109.5. So pH3 will be a trigonal pyramid with a bond angle of 109.5. And actually what is observed is that the angle is slightly smaller and closer to 107 degrees. The molecule below is ozone, O3, formula O3. 3 oxygens bonded together, and the central atom is the oxygen in the center. It's surrounded by a single bond, a double bond, and a lone pair. So that's 3 electron groups. 3 electron groups with 1 lone pair. So let's look at the. So 3 electron groups with 1 lone pair. You look at the line where it says 3 electron groups, 1 lone pair, and the molecular geometry is bent. Right, the lone pair makes it look like a bent molecule with an angle of 120 degrees. So ozone has a bent shape with an angle of 120 degrees between the 2 bonds. Now let's look at CCl4 to the right. CCl4, carbon is the central atom. It's surrounded by 4 single bonds. And so that's 4 electron groups. No lone pair. And so 4 electron groups, no lone pair. So 4 electron groups, 0 lone pair. That's a tetrahedral molecular geometry. And the bond angle is 109.5. So it's our tetrahedron there. So CCl4 is tetrahedral with a bond angle of 109.5. Finally, BF3, the molecule at the bottom right. So boron is the central atom. It's surrounded by 3 single bonds, no lone pair. So let's look at the table. So you look at the line that says 3 electron groups, 0 lone pair, and it's trigonal planar. So with a bond angle of 120 degrees. So let's go back here. And so BF3 is a trigonal planar molecule with a bond angle of 120 degrees. So it's a flat molecule. And so notice how all those shapes we've mentioned here, the Lewis structure here is not showing those shapes, right? Ozone is not bent, the BF3 is not trigonal planar. You know, the CCl4 is not drawn as a tetrahedron. Only the linear molecule, you know, you cannot change the way you would draw it. But all the others, you would have to redraw the molecule to show the shapes that you are deciding that it is.